Okay, so now we're going to be discussing about equivalent resistance, capacitance, and inductance. Now, just in general, we're not going to be discussing about the formulas that lead to this, but rather just then the observation. So resistors look like this. If you have taken a little bit of physics, capacitors look like this, and inductors look like this. Resistors model any kind of obstructive pathway in which the flow of electrons is not as easy, whereas capacitors are modeled as two parallel conducting plates in which in which a potential creates an electrostatic field storing electric energy. Inductors are modeled as coil shapes which have current carrying capabilities to induce a magnetic field, storing magnetic energy. For this discussion, we're just going to be discussing about their equivalent resistances when they are two or more of that same element, and just so we can see just how they're able to be combined in general. Okay, for resistors, whenever they are connected, we have to ask, are they connected in series or in parallel? These two, as mentioned from the discussion about series versus parallel, are in series. So as such, their equivalent resistances are R1 plus R2. While in parallel, we have to check that they share the same simple node, or they have two shared simple nodes, and their equivalent resistances are therefore R1, R2 divided by R1 plus R2. And just so we're clear, R1, R2, R1, R2. What about capacitors? Well, capacitors, when measuring relative to itself, are actually reciprocal to, or actually inverse to to resistors and inductors. So their equivalent capacitance in series is C1, C2 divided by C1 plus C2. C1, C2. When they're connected in parallel with C1 and C2, then they have then they add together. Actually, because of this property, we would want to connect these in parallel as a way to decouple. And this would be important to kind of lower the, lower the angle so that we can increase the power factor. Finally, for inductors, we have two inductors in series that combine like they would for resistors. So LEQ is L1 plus L2. Whereas for if they're in parallel, L1, L2, we would combine them as we would with resistors in parallel. L1, L2 divided by L1 plus L2. Now, as a challenge to the viewer, I request that I challenge the viewer to come up with a generalization for when you have an N combination in parallel or in series of the same resistors, capacitors, or inductors. Now, as a word of caution, you can only combine if they are the same elements and along that same branch. So, can only combine with same type of element. And I have to put an asterisk next to it because we will actually violate this rule later on. So first, if you had a resistor, a capacitor, and maybe an inductor, you can combine none of them. If you had a capacitor and an inductor, and maybe another inductor, which is in parallel with this resistor, you can combine none of them. Now, what is this asterisk for? There's only one condition in which you're allowed to do so, and that would be considered when you consider their impedances. So if you consider this as some kind of impedance fact, so impedance, 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 and impedance, only then you're able to consider that they are able to be combined in series and parallel, because when they're all considered as impedances, they're all modeled as if they were just a resistive element, and therefore you're able to combine them with no issues. So I hope this helps you understand how to combine elements like these in in series or in parallel, and as well as a discussion as to why you can't combine different elements in series or in parallel unless they are considered as impedances. Okay, thank you.